Hi, class. This is Mr. Hart. In this podcast, I just want to go over some of the material we covered in week 3 on motion. And if you are making this up for participation, let's try and answer these questions here. So, for example, a man drops a watermelon off the top of a building. It takes 7 seconds to hit the ground. How tall is the building, and what speed was it going when it hit the ground? Okay, so if you watched the podcast from last week, you should be able to answer this problem. So, if you're making a participation, go ahead and answer that. But this week, we are going to talk about two-dimensional motion. Okay, so every problem we've done so far was just in one dimension, right? An object falling straight to the ground, a car going across the road. Okay, everything we thought about is in one dimension. But now we're going to look at two-dimensional situations. So, for example, a cannon shooting a cannonball off a cliff. Can we still tell how tall the cliff is? Can we figure out how far the cannonball is going to go? Well, it turns out with physics you can. So here are the equations we can use to figure this out. So it turns out our height is still going to be the same. It's just a free fall equation, 1/2 gt squared. Okay, that's how we calculate the height. But the distance that the cannonball is going to go, we can just use our velocity equation. If we rewrite it, we get this. The velocity in the x direction times the time will give us our position. Okay, so looking at this cannonball scenario, if we want to find the height of the cannon, okay, then we just need to know the time it takes for the cannonball to hit the ground. Okay, and if we want to know how far this is going to go, we just need to know the velocity of the cannon that it shot it out at, okay, and then the time it takes again to hit the ground. And this is really nice because in physics, it turns out that the y direction, okay, and the x direction are completely separate. We can treat them separately in the equations, okay, which is why we get these two separate forms. Okay, so these equations will help us to answer this problem. So for example, if we look at the cannon that shoots a cannonball 40 meters per second off a 50-meter tall cliff, okay, if we want to figure out how long it takes to ground, we will just plug it into that y equals 1/2 gt squared equation. Okay, that's the free fall equation. So we know the height of the cannon. We know g, 9.8, so we just have to solve for y and plug in t. Or sorry, solve for t and plug in y. Okay, that will tell us how long it takes to the cannonball to the ground. And then if we want to know how far the cannonball went, we just take that other equation, x equals vx. Oh, excuse me. Let me rewrite that. So we get x equals vx times time. Okay, so this vx right here comes directly from the problem, this 40 meters per second. And again, sorry that I don't have a better writing utensil. Okay, but this is directly from this 40 meters per second. So we'll plug that in for Vx. This time we'll get from solving this equation, and we'll plug that into there. Okay, and we can figure out exactly how long it takes to fall and how far the cannonball went. Okay, so go ahead and do that if you are answering this question for participation. Try and figure out the height and the distance, or try to figure out the time and the distance the cannonball went. Okay. And if you want to try another one, you can also do this one right here. Okay, same problem, but with just slightly different numbers, 30 meters per second and 20 meters tall cliff. So try both those and see what you get. Okay. All right, then we looked at another situation. Oh, actually, we did the hit the target lab. If you need to do that, go on the website and you can find that. But then we looked at another situation, okay? Suppose you were a B-52 bomber pilot during World War II, okay? And you were assigned to do a bombing run on an artillery outpost, and you're approaching the target, okay? So you're in the plane, you're approaching the target. How would you figure out when to drop the bomb that you have? When would you decide to start dropping the bomb, okay? So if we look at a visual, right? Here's the plane coming by, the B-52. When do you decide to drop the bomb? Do you drop it when you're in the A position, the B position, or the C position? Okay. Now, some might be tempted to say, hey, in the B position, you'll drop it, it'll fall straight down. Okay. But that's not the case. Okay. We actually want to drop it when we're at the A position because the bomb is going to take an arched path. It already has some motion going with it. Okay, so it's going to fall along this arched path. Okay, so this turns out to be exactly like the cannonball situation, except now we have a bomber plane. You just say, here's the height above the ground, here's the speed it was moving at, or the velocity. How far away from the target should the plane be? So you plug it in, again, just like before, solve for time, solve for the velocity, or solve for the position, and there you go. You can figure out how far away from the target you should be. And I think if you plug this all out, you get something like 1,000 meters. I can't remember the exact number. Okay, but it's pretty far away. Okay, it's close to almost a mile away, I believe, when all is said and done, that you want to drop these bombs. Okay, so if they were a fighter pilot, okay, or a bomber pilot during World War II, they're dropping these bombs almost 1,000 meters away, which is kind of crazy to think about, but it's true. Okay. Anyways, if we move on, we watched a little plane example of them dropping the bomb, and we discovered something interesting. From their point of view, they see the bombs going straight down, okay, which is often what you see in movies. You see the bombs going straight down in the old movies and the old footage, okay? So why do they see it going straight down, and why do we see it going at an angle or going along that arc? Well, it turns out that they have a different frame of reference, okay? So this is one of the vocabulary terms. A frame of reference is the observed velocity of an object that's dependent on the velocity of the observer, okay? So what that means is how fast you see something moving, or how fast you see something moving, is going to depend on how fast you are moving and which direction you're moving, okay? So for example, from the tank's perspective, okay, in this situation, they see this arced path, and we see this arced path. The bomb comes along the sky, comes down, and hits them in this arch as the plane moves along. But from the plane's perspective, because they're moving, they see the bombs dropped, okay, but they're moving the same speed as the bombs, okay, so they see them going straight down. And from their angle, it looks like the ground is moving, or the artillery is moving towards them, and so they are just timing when it's going to hit, okay? So there's this perspective from the tank or our angle, and there's the plane's perspective, which is why we always see them going straight down in the movies, okay? Because they have a different frame of reference. They see the velocity differently because of where they're at, okay? And so it turns out in physics, it doesn't matter which frame of reference you use. As long as you do the math right in that frame of reference, your answer will be correct. So it doesn't matter which frame of reference you use. Most people end up using a stable frame of reference, or like the Earth's frame of reference for most problems. But you can do problems from this perspective and still get the same answer. Okay. So when we think about using frames of reference, we can usually think about in a simple equation that the velocity that we see is dependent on our velocity, the velocity of the observer, and the velocity of the object. Okay, so we add the two velocities together to get the velocity that we see. Okay, so for example, let's say we have someone on a car or a truck or whatever it is riding along, and they throw a baseball off that truck. Okay, so if the car or the truck's moving 30 meters per second, and they throw the baseball at 40 meters per second, then the speed we're going to see the baseball move is going to be 70 meters per second, okay? Because both objects are moving that direction, we're going to get a combined velocity of 70 meters per second in our perspective, okay? Likewise, in the other direction, if they throw it this way, we're going to get 30 meters per second minus 40 meters per second, so it's going to look like it's going 10 meters per second that direction, okay? So if you're answering this problem for participation, or if you're watching this podcast for participation, answer this problem below. Okay, so you see a boat going down the river that flows at 10 meters per second. If the boat engines are pushing at 20 meters per second, what will the actual speed of the boat be in your frame of reference? Okay. All right, and so we had a homework, I believe. Yeah, we have a homework on frames of reference, and that is all we talked about for this week. We also talked about conversion factors, but I will do a separate podcast on those. So if you have any questions, let me know, and thank you for watching.